Welcome to aminacademy.com. In heat and mass transfer, let us discuss about heat conduction through plane wall with uniform thermal conductivity. Look at this figure. A plane wall with length L is given through which the heat is flowing in x direction only. Suppose L, thickness of the plane, wall. A equal cross-sectional area of the wall. K equal thermal conductivity of the wall material. T1 and T2 temperature maintained in phase 1 and 2. Maintained in phase 1 and 2. Here temperature T1 is here and phase 2 temperature is T2. Now general heat conduction equation dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square plus Qg over K equal 1 over alpha plus 4 alpha into dou T by dou tau. Let it be equation 1. If the heat conduction takes place under the condition steady state and steady state, I can say dou T by dou tau equal to 0. That is one dimensional. Therefore, I can say dou T square by dou y square equal dou T square by dou z square equal 0. That means only in x direction heat is conducted we consider, and no internal heat generation means Q of G over K equal to 0. Then the above equation becomes, therefore, one gives therefore the equation becomes like therefore the one dimensional, these all zeros, dou square T dou y square dou square T by dou z square equals 0, and no heat generation Qg by K equals 0. Then the above equation reduces to dou square T by dou x square equal to 0, dou square t by dou y square equal to 0 by integrating we get above equation twice. We get dou t by dou x. Dou t by dou x equal C1, and further integration t becomes C1x plus C2, where C1 and C2 are arbitrary constant, where C1 and C2 are arbitrary constants. Therefore, substituting the equation, therefore we are having T1 equal 0 plus C2. We are substituting in, this is 1 first, this is 2, we can keep it, this 2. Therefore, equation 2 becomes T1 equals 0 plus C2 and T2 equal C1L plus C2. Now, after simplification, we'll get after simplification, we get C2 equal T1 and C1 equal T2 minus T1 by L. Therefore, T equal, therefore the equation therefore the equation 1 becomes, reduces to T2 minus T1 by L into X plus T1. Let it be 3. Now, this equation indicates the temperature distribution across the wall is linear and independent of thermal conductivity. Here, this is a linear and temperature is independent of thermal conductivity. Now, heat through the plane wall can be found by Fourier's equation. By Fourier's equation, we are having Q equal minus Ka dt by dx, where dt by x is temperature gradient, where temperature gradient. Now, but we can put dt by dx equal d by dx of, you are substituting t values, t2 minus t1 by L into x plus t1, which is equal, This is equal by differentiating gives T2 minus T1 by L. Therefore, Q equal, we are substituting dt by dx, that is here minus k, minus become plus k, and we are changing this position T1 minus T2 by L. Here A is there, Ka. Therefore, we can write Q equal T1 minus T2 over L by Ka, which is further you can write T1 minus T2 L by Ka equal thermal resistive resistance of thermal conductivity, thermal resistivity. Therefore, here where RTH equal to thermal resistivity of the material. Thermal resistance of a heat conduction or thermal resistivity. Thermal resistivity, no, thermal resistance. Now, let us find out the condition when instead of a space, weight is the main criterion for selection of the insulation of the plane wall. Thermal resistance, that is L by Ka we did, then eliminating L. Now weight of the wall, that means full wall considered, that is W equal rho density of the wall A into L, rho into volume. Therefore, eliminating L from 4, suppose let it be here, eliminating from, that is the equation RTH is L by Ka, we get W equal rho A into R thermal resistance of conduction into Ka. So which is equal, therefore W equal rho K A square into R thermal conductivity of conduction. This is the weight of the wall we have to select for the particular temperature difference. We have done. Please subscribe our YouTube channel.